So last time we talked about going backwards, and we're going to keep, that's basically the second part of the course. But it's kind of like finding a derivative. The purpose of that was so we could talk about rates of change, and so we could talk about slopes at an instant. So now what the purpose of our second topic is going to be talking about area underneath the curve. And it's not just the geometry of that has some application. There's tons of different applications to that, trying to find out what the area underneath the curve is. For example, if I was to show you a curve that looked maybe like this, and tell you this was someone's distance and time, if I was to shade underneath the curve, can anyone make you want to make a wild guess what I'm going to get if I was to figure out how much area is under there? Velocity, if this was distance versus time, is the tangent, right? Because that would be the change in distance over the change in time. Yeah, it's actually going to be the total distance. If you don't, it's obvious. It's not something obvious, but if you pick a simple graph, right? Let's just pick a square, I guess. Okay, sorry, this should be velocity, not distance. Okay, then let's just say this is, to keep it simple, 10 miles per hour, and this is 2 hours. Then, common sense says to you that 10 times 2 is 20 miles, but that's also the area in here. So when it's not just a simple straight line, you can also find the total area under the curve for things like this problem and many, many others. So that's what our job is today, is to take our first look at area. Now, I used to go a little heavier on theory, but I've backed off of that a lot lately. I'm trying to give you more of a practical understanding of it, but I will still introduce a little bit of those ideas here. So first of all, if you were to consider an upper and a lower limit, what I'm saying is you would pick the largest area underneath it, approximating it with rectangles, and the smallest area. So if I looked anywhere between here and here, the reason this point was chosen is it makes the biggest rectangle. If I always pick the biggest point, I'm going to get the most area. So if I wanted to approximate it, I'd keep picking the biggest rectangle, and this would be my upper limit. Every other approximation has to be less because I've always picked the tallest rectangle. This one is the opposite. It's picking the smallest rectangle for every approximation. So this is the lower limit. Every area has to be bigger than this. And what we're doing here is, if you add up these green areas, it's approximating this here. So if you added up all of this, you'd be approximating the real area under the curve. So how do you think we get from approximating to exact? What would you have to do? That might give us some, there might be some patterns where that actually gives us an answer, but unfortunately that would be limited in our discussion.
Maybe like as opposed to average?
So I think that's what Leo was getting at with an average, and that would work for straight lines and things, but not exactly for, it's just not a versatile technique. But what I'm saying is, if you wanted to approximate the area with rectangles, how would you make it more accurate? And then how would you take accuracy so that it was exact? More rectangles. How many more? An infinite amount, right? So if you had an infinite amount of rectangles, that's what you'd have here with this area. So the only theory that I'm going to hit you with right now is that you can pick anywhere you want, because if you have an infinite amount in the upper limit and an infinite amount in the lower limit, they'll end up in the same place. So whatever strategy you pick, as long as there's an infinite amount of rectangles underneath that curve, you'd be able to come up with the exact area. So you're free to choose wherever you like. And I'm going to show you a couple of the techniques that we use in choosing those areas. Okay, so this time we're going to do an upper limit from -2 to 1. So here's -2 out here, and here's 1 out here. Now what I'm going to draw for you in purple is the exact area. That's under the, sorry, should have had some coffee this morning. That one wasn't underneath. That would have been just gone on forever because it was anywhere it wanted above the curve. So that's the exact in purple. But if I use 3 rectangles and I want to approximate this with its biggest one, here's the 3, well, first, the distance from here to here is 3 units. So each rectangle has width 1. So that's how I know the first one I'm going to put in looks like this. The second one I'm going to put in looks like this. And then the last one I'm going to put in, oops, looks like this. I'm going to switch to a thicker pen here just a second. Okay, so those green rectangles, because it's a negative, this is the largest value. This one is -2. The other one down here is -3, so that's the biggest one I can pick. This one here is 0, and this one here, of my choices, there's a 0, there's a 2. So I'm always picking the biggest value. That's why I'm all the way up here at 2. So the area in here is 1 and -2 here. So the area is a -2 when you multiply them. The area here is 0. And the area here is width 1 and height 2. So it's 2. So the area using the upper limit would be -2 plus 0 plus 2, which is 0. Now if I use the lower limit, I'm going to pick the smallest value. So again, this time my first rectangle has to be somewhere in here. The smallest value is this one down there. The second rectangle is somewhere between here and there, and this is the smallest value. So that's the smallest I could come up with. And then in this range from here to there, that's the smallest value is, there's no area because it's flat. So if I wanted to add them up, I have a width of 1, and this one has a height of -4, so its area would be -4. This one has a width of 1, and it's -2 here for its height, so it would be a -2 for the area. And then the last one here, there is no height, so it would be 0. So right now I come up with -4, -2, and 0. So a lower limit would be -6. So basically, I haven't done a lot of work on this, but I know that the real area is somewhere between 0 and -6. So now we're going to try doing the actual area itself. And this was the one that we talked about, is they are equal when the rectangles are infinite. And if I wanted to then find the actual limit, the actual area under there, I'm going to have to use limits to do it. And before you freak out, this is probably the last time we'll use limits to do it, but let's take a look at how we could build this up under the curve from -2 to 1. It's always good to have a picture so you have some idea of what you're looking for. So let's draw the picture again. I'll just put it in my margin here so we can work with it. Okay, so now we can't talk about any specific rectangle. We have to talk about having n rectangles. So the area for each rectangle, if we take a look, because I can pick any way I want, I'm going to pick equal widths. So let's see, what could I do for widths? If this is -2 and this is +1, then the total here is 3. So each rectangle gets 3 divided by n for the width. So if I have 100 rectangles, it would be 3 divided by 100. If it was 3 rectangles, 3 divided by 3. I'm just dividing it up equally amongst those rectangles. And I also need to come up with, so now I know how wide the rectangle is, but I also need to come up with how tall it is. So because I picked equally spaced intervals, they're going to look something like this. Maybe the first one's here, next one, next one. They're going to be at predictable spots as I move along because it's equally spaced. So that's what these points are here. It's just a little shortcut of how you find it. The first point here is -2. And if I had, say, 5 rectangles, I'd have to move over by each one of these from here to here. That's the delta x that you move over. That's how much I move over to get there. So if I wanted to get to a certain point, I just have to figure out how many spaces I've moved over. So I'm going to choose the right side, which means any point on the right. Maybe I'll zoom in here, it's getting a little cluttered. If I choose the right side, that means I'm always choosing, well, that dot's going to have to stay there. I'm always choosing points to the right. So here's the first point here if I'm moving to the right. Here's the second point. Here's the third point. Fourth point, and so on. So how do I get it is where I started was at -2. And then if I want the first point, it's 1 times how far over I moved. If I want the second point, which is this one right here, I started at -2 and I had to move 2 of those delta x's. And each delta x is a rectangle. So that delta x is this 3 over n. Okay, so that means I have -2 plus, we're using I here as just our formula. So I know it looks bad, but basically what it means is you tell me how many rectangles you want to approximate it with. So someone give me a number. 50? 100. Okay. So for n equals 100, you're dealing with the special case where you'd have -2 plus I 3 over 100. And what I tells me is where, which number rectangle I'm on. So if I'm on the 5th rectangle, I put in I equals 5. The 6th rectangle, I equals 6. And I go all the way up to the 100th rectangle because in this case we have 100 of them. That's the number that someone threw at me. So the area is going to be to add up, and that's sigma notation. Have you guys seen sigma notation before? Okay, don't worry too much about sigma notation, but this is just lazy mathematician way of saying the sum. It's capital Greek letter S, so it's used to abbreviate the sum. And if I start at 1 and I go to n, it's going to be, I'm adding each of the rectangles up. So the width of each rectangle is 3 over n. and the height is going to be my function at -2 plus I times 3 over n. And my function just multiplies by 2. So I could update this. So I'm going to tidy this up a little bit. That means my area is from I equals 1 to n, 3 over n, so it'll be -4, and that'll be 6I over n. I'm even going to go a step further here, and I'm going to separate these things out. And I'll tell you why in just a second. So I wanted to distribute there. So these are the this is the formula that if you tell me how many points you want, now I have to add them up. So I'd have to do this 100 times in Leo's example where he said, let's try it for 100 rectangles. Our goal is going to be to get to an infinite amount, right? But luckily there's some formulas to shortcut this for us. So these two pieces, it'd be the same thing as summing up from 1 to n of -12 over n plus the sum from I equals 1 to n of 18I over n squared. And I'll kind of tell you how the first one goes so you understand the first formula. If I'm going to add, let's just say we pick the number 10. Okay, I'm going to add this number up 10 times. So I'm going to see it 10 times. So whatever that number is, it's just going to be the same as multiplying them. It's like taking the number 5 and saying add 5 and go 5, 5, 5, 5. You just keep adding it however many times you had. So that'll be -12 over n, and I'm going to see it n times. This one's a little trickier. So the one that we're looking for is this one here. I want to know what's the sum from I equals 1 to n of I. And the shortcut I get here is it's n times n plus 1 over 2. That's number 2 in the textbook of the formulas. So that's what I'm going to replace this summation with. This summation then is going to become 18 over n squared. And the way I'm recognizing it is when you give me that number for n squared, this is just a constant. So it's almost like the only thing I'm dealing with is a constant times I. That's how I knew which formula I was going to. So this is going to be times, sorry, it's pen sticking, n plus 1 over 2. And I can simplify that as well. So let's see what the simplified version is. Here the n's would disappear and I have -12. And this 18 and 2 would become a 9. On top, I'm going to have n squared plus n, and that's over n squared. So this piece is going to be -12 plus 9n squared over n squared plus 9n over n squared. So I have these would be divided out, and I would get negative 3 plus 9 over n. So that's my formula. I've gone through all that work because now you can tell me, well, I would like to have 1,000,000 rectangles, and all I need is a calculator. I put in 1,000,000 for n. What's going to happen as I go off to infinity? Uh, 9 over n becomes 0 as I go to infinity. So this part here, as I go to infinity, this part is gone, right? So the exact value would be negative 3. The area underneath that curve is negative 3. So here's the good news. The remainder of the techniques we do are so we never, ever, ever have to do that again. But what you need to know is there's still going to be times when you're asked to think this way, not in terms of infinite limits, but that before we have these techniques, we're going to be approximating areas by adding them up as rectangles underneath the curve. But there'll be much simpler examples, I promise. But this is exactly what was done until these techniques were developed that I'm about to show you. And I promise you, they're nothing like this. They're much simpler to do. It's akin to when you first started derivatives and you saw how to do it with limits. And now you're like, God, why did you even make us bother to do that? Because that was so much harder than just learning the rules, right? The rules are coming that make life easy, but just know and appreciate that this is where they started, these infinite limits on rectangles under a curve. So we have a notation for this. This whole process of finding that area under a curve by adding them all up is known as a definite integral. And it is saying you're going to take an infinite number of rectangles. This is the height. This is the width. That width is delta x, and the height is how tall the function is. You're adding them up. That's the summation, an infinite number of times. So that definite integral, instead of writing all of that stuff out, we have a shorthand for it that looks like this. It's this squiggly line here, which we've been calling antiderivative. Now we will refer to it as integral because in this case we're saying the integral from a to b of f of x with respect to dx. So this is, again, the notation we're using is saying this is looking for the area underneath the curve from a to b. It represents all that nonsense that I'm hoping that we get to avoid because it's messy. And I just had a former student from UBC actually tell me that they were making them do this. And anyways, I had to calm her down and say, remember, they're not going to make you do this all the time. You can relax. You'll be on to better things later. So know that if you see it again next year, it's going to go away just like limits did too. But at least I get to be the first one to torture you with it. Okay, so for now, we're going to use geometry to help us get through these definite integrals because that's a lot easier than having to do the limit process. Again, our goal is to avoid that limit process and never have to use it again. So if I said, this is your notation, can somebody just refresh our memory? What does it mean? Okay, that's how you would read it. This is the integral from -2 to 1. But what is it asking for? What does it represent? The area under the curve. Thank you. So what it represents then is this area here. From -2 to 1. So when we started with derivatives and I said, you see a derivative, you think slope of a tangent or instant rate of change. Now when you see an integral, you think area. That's the first thing that comes out of your mind is area. What's the second? Well, you know what? I've probably blown your cerebral cortex already. I'll leave you alone for a few minutes here. The second thing that you should always think about is what does the integral represent? It represents a sum. There are some problems that we do where you're adding a bunch of things up and you'll be going, oh my God, what is this? Because if you only think about it as area, you're missing out on the point. And the point is that It gets the area by adding up an infinite number of rectangles. So the problem you're reading might not be about area. It might be something else. If it's a summation problem where you're adding a whole bunch of things together, it could be that you're looking at an integral, most likely. So those are the two things you got to remember for integrals. Area is the picture in your head, and summation is the thing that it could also represent, because that's what's happening underneath the hood. So if we use geometry here, can anybody give me, let's call that triangle 1, call that triangle 2. Can anybody give me one of those triangles? Sure. So it's a good thing for me to clarify then. The height is always taken as the height of the function, because this is where it comes from, the height of the function. So you're absolutely correct here. The height of the function is negative. It's all below the axes in this triangle. So we would take it as -2. But the change in x, it's a positive change. It keeps increasing. As we move this way, the change in x is positive, right? So that means I'm going to have, oh, sorry, that's a -4, not -2. So this width here is 2, okay? It's possible that you run the x's in the opposite direction. Maybe you're doing a problem and you go this way. What would you have to change? Yeah, what happens to the 2? It'd become a negative because now your change in x is going negative as well. Okay? But this time, we're looking at it. Its area is going to be 1/2 base times height. So that's going to be -4. Now, the other thing about interpreting what this means is you're looking at the area underneath the curve, and that area is underneath the x-axis. See how it's all down there like that? So we're expecting it to be negative for this one. The only way you could get it positive is if you walked backwards 2 when you did it. So it would be a negative of a negative, and then you get a positive. But this next one here, it has a width of 1, and the function is positive all the way in it. So it'll have a height of 2. The area will be 1/2 base times height, which is just 1. So using geometry, we add up those two triangles. -4 plus 1 is -3. So we can answer that integral using the geometry formulas that you hopefully don't forget. I might be nice enough to give you the area of a triangle if you ask. The AP examiners won't. But see what you can do on this next one. If it's not clear to you, that is a quarter of a circle there. That's a, it's not a semicircle. What's that? What would a half of a quarter circle? Anyway, that's what it is here. The rest of it are line segments. So see if you can find out what that integral would be using geometry. How many people approach that as a rectangle and a triangle? Yeah, no problem. There is a geometric shape for this. Do you know what it is? Yeah, it's called a trapezoid. So again, you can still do it with rectangle and triangle, but the way you get it is you have to average the top and bottom there. So it would be top plus bottom over 2 times the width. So the top here is 4, the bottom here is 1, and the width is 2. So I'm going to get, let's see here, 4 plus 1 over 2 times 2. So I get 5. And then this piece here, it's a width of 2, a height of 1, so the area is 2. So altogether that area is going to be 4 pi, and I have 7 more there, so 4 pi plus 7. And the great thing about the geometry is you could also have interpreted it this way, and that would make some sense too if you thought about take that whole rectangle out, take that triangle out. That's fine too. So this task of using geometry is not just a novel purpose for us. It's also something that the AP exam would have you do to show, that you understand the concept as area under a curve. There may be a function that you're looking at that's either not given or very, very difficult to use our techniques to find, and it could be that geometry is the way to go. Okay, so properties of integrals, you definitely need to know these. The first property, let's see, what do you think? If I go from A to A, how much area do you think I'm going to get? Good. So I get nothing because I haven't moved anywhere. I don't have any width underneath the graph. So there's no area. That's an empty integral. What happens, do you think, with a constant? Well, a constant's really just a bit of a distraction. It can be taken outside and we can ignore it. It's the same thing like this if that helps you find the integral. The constant can be pulled out. Same as it can be in an antiderivative, same as it can be in a derivative. Same as it can be in a limit. Now here's an interesting one. If I go from A to B, I can actually get the negative of it. How do you think, how could I do that? With just the information I gave you, how could I make it negative? B to A, yeah, I go backwards. So if I went from 1 to 3, that means I'm moving to the right. The change in x is a positive number. But if I flip it, then I'd be moving from 3 to 1, and I'd be going negative. I'd be going backwards. Yeah?
Why is the second one, the F or second trapezoid?
It's not. It's just, I can make it rounder if it doesn't look.
Not this one, the one on the left.
This one?
Yeah.
It still should be round. It shouldn't be a big F. Okay, and then finally, well, I guess there's one more after this, but again, hopefully this is more of a common sense one. Picture that you have a graph that you're trying to find the area under. You've already actually done this. If this is A, and let's put a point in the middle. What do you think? Could you figure out a way of splitting it into 2 pieces? Because now there are 2 integrals. How could you do that? Yeah, we're just going to take the area here, that's part number 1, and add the area here, that's part number 2. So this would be from A to C, and C to B. So the reason that's important for you is when it's convenient, you can split the integral. That's exactly what we did up here. Right? When we did this example, actually even when we did this one, it was convenient for us to split those into different pieces. And that's all this one says here too. Okay, and then finally, if you have more than one function that you're integrating, like f of x plus g of x or minus, you can just rewrite that. It's the same way you had it. You can separate them if it's convenient as well. Okay, so again, our techniques we're going to develop for the moment. We're no more limits come across your desk for the time being. The ones I have here you should be able to do from the picture. Okay, so you can use the laws I gave you if it's helpful. You can use the picture. Let's see if you can find those definite integrals that I've given you. So for the first one, you could pick it as a rectangle and a triangle. That's fine. Otherwise, you could pick it as a trapezoid, and you would get 5 plus, well, anyways, you end up with 21 over 2. You could also, if it really freaked you out to do it this way, you could find the integral from, oh, my apologies. Anybody notice something different about this that I didn't? I skimmed it real quick. You didn't notice it too, so it's... Oh, okay, well, so I guess it is my mistake. Yeah, there is a 3 to 0 this time. So the direction I'm moving is backwards. So that means the area is going to be the negative of the one I'm used to. So that needs to have a negative in here. So again, I'm going backwards. The only way to get from 3 to 0 is to have negative x's bring you there. So the change in x is negative all the way. Okay. And then for the absolute value graph, that's how we've been dealing with this graph since we first started using it, was to break it into pieces. So it would be convenient for us to make the pieces go from -1 to 1. So this is the same thing as the integral from -1 to 0 of negative x dx plus the integral from 0 to 1 of x dx. And then I can just focus on these two pieces I get, which is here and here. So the first piece, that has an area, that's 1 by 1. So 1/2, 1 times 1. And similarly for the second piece. So each one has a half. Altogether, they're worth 1. Okay, so symmetry can also help us out. If you were to do this, not having any other better techniques, well, you'd probably be stuck. Unless you use some imagination here. Can anybody think about why this is an easy question? It's not actually a hard question.
This is just a circle.
I'm not sure what you mean. It's not quite a circle. The graph, like, you mean this? That's a circle. Yeah?
It's an equal wave, so you could just go in between and make it into a rectangle kind of thing.
Okay. You're on the right track, but I'm not sure that you're describing it properly. That's all. But that's okay.
It's a sandwich shape. Let's just start like that. You flip the ball apart. It'll be like honey, right?
Nope. Not necessarily. You're being very creative about this, about flipping circles around and other things. Take a look at it. I'll do my best to... Oh, it's 0. How come? Oops. Yeah, it's just equal to 0 because we have as much above as below. The graph has symmetry there. Okay. So if you have a symmetrical graph, they would cancel each other out like that. Okay, so anyway, today as our discussion goes, what you should now know is that lots of blood, sweat, and tears went into avoiding limits, but they do exist underneath what we're doing. That you'll be using geometry to find definite integrals, and those represent area under a curve.